On the 5th of July 1687, Isaac Newton published his laws of universal gravitation in his book Principia, which stated that the force between two objects is equivalent to the gravitational constant, the mass of the primary object, and the mass of the secondary object, multiplied together, all divided by the distance between them, or radius, squared. This rule held up for over 200 years, until the early 1900s. In 1907, Albert Einstein introduced the principle of equivalence, stating that somebody accelerating upwards should feel exactly the same as someone in a gravitational field. Imagine being inside a box, with no windows or holes to look out of. You feel pulled towards the ground as if you were standing on Earth. Despite the force you may feel, you can't actually tell if you're on the surface of Earth, and not accelerating through space at 9.81 meters per second squared. Now, you may be able to tell the situation you're in depending if the force at the top of the box is less than the force at the bottom due to their varying distances from the center of the Earth, but aside from this, there's no experiment that can be done to distinguish between being affected by a gravitational field or accelerating through space. After realizing this, Einstein also came to the conclusion that light should be curved by a gravitational field. He said that if the person in the box shone a light across the box, it should, obviously, travel in a straight line. But the inside viewer wouldn't observe this to be true. That's because as the light travels in a straight line, the box also accelerates upwards, making it appear as if the light is forming a curve. And because of this principle of equivalence, this light should also appear to bend in a gravitational field. After Einstein completed and published his theory of general relativity in 1915, it was 4 years until his idea of light bending in a gravitational field was partially proven through experimental observation. During the 1919 solar eclipse, the moon blocked out most of the glare of the sun, allowing stars behind it to be observed. The observations were done by Sir Arthur Eddington, a well-known astronomer at the time. He observed that the stars seemed to be displaced from their regular position while the sun was nearby. Einstein explained that due to the sun's gravitational force, the light from the stars were being bent and redirected, causing them to appear in abnormal positions in the sky. Einstein's predictions matched the observation. However, there was one new problem that arose from this experiment. Newton's laws of universal gravitation were being broken. His equation stated that the gravitational force between the two objects was equivalent to the gravitational constant multiplied by the mass of the primary object, in this case the sun, multiplied by the mass of the secondary object, in this case the photon coming from a distant star, all divided by the square of the distance between the two objects. But there's one problem. The photon in this equation has no mass. No photons do. So, if you run the equation, the force between the objects will come to zero, and Eddington's observations are not consistent with this. Does this mean that Newton was wrong? Not entirely, because his equation usually predicts the outcomes of both scenarios very accurately, but when it gets down to really precise measurements and massless particles, his ideas about gravity just don't work. So, what does this mean for gravity? Is it really a force? Newton said yes, but Einstein proved that this wasn't really the case, showing that the force was really just an illusion, the reality being that mass had an effect on space-time, distorting and changing the paths of other objects.